Hey guys, what is up? It's your pal Dave back live in the lab. Doing stuff, building things, you know, the usual stuff. So, what am I doing today? Well, boy, are you guys in for a treat, because today we are going to look at data sheets. Yes, because as you may know, I've been working on this Teensy based board with Midi input and output, and I've come quite a ways on it, but I have to finalize the Midi circuit. And as you may know, the Teensy is a Arduino. Let me get you a better view here. Let's see. There we go. The Teensy is a Arduino compatible board. It's got some nice features above the Arduino, so that's why I'm kind of switching to it. But one thing is it does run on 3.3 volts instead of the normal 5 volt. Hey, who's in the chat? Joseph C. Hello. Welcome. Nice to see you. So this guy runs on 3.3 volts, right? MIDI and most things run on 5 volts. So we're going to have to do some configuring to make this work properly. So let's go back here. So what are we doing? We have to figure out how to make a 3.3 volts device. Who's there? William. Talk about good timing. I just bought a Teensy and various audio things. Awesome. So join the club. Welcome. So maybe together we can work some of this out, because it's, you know, there's a lot of different information out there. And who's that? Akash? You as well? Wow, all the Teensy guys are here. Nice. Okay, maybe together we can put our heads together and come up and kind of make ourselves into one intelligent person and figure this stuff out. Because man, it is complex sometimes. So yeah, so we got to get a MIDI circuit that's compatible with 3.3 volts. Okay. Now let's see. Here's the optocoupler I usually use, which is the 6N138. Now before we dive into this, let's do a little background on how some MIDI stuff normally works. So let's do a little sketching here. So a normal MIDI output circuit, if you may know, if you've been following my channel, is a plus 5 volt source that goes into a resistor. Nice resistor. All right. And that connects to a MIDI jack. It goes out into the world, into your MIDI receiver, and then comes back through another resistor to, we'll call it 0 volt or ground. And we're going to kind of quantify that a bit in a minute. Now, to complete a MIDI circuit, what we have to do is kind of look at the whole thing. So pretend this is your MIDI jack. So there's your MIDI jack. There's cables up to 50 feet connecting this to the other circuit. All right, so in here is your cable. Now on the other side, we have, coming from the MIDI in jack, we have a resistor. And that goes to the optocoupler input. And we can think of that as just an LED. And then that goes back to the MIDI jack. So this is the MIDI out circuit from one device. This is the MIDI in circuit from another device. And just to make it clear, this guy here is part of our optocoupler. So let's say it's a 6N138. Okay? And that kind of looks, here's one here. It's just a little microchip on the board. Okay. Hey, who's that? Cirque Stoffer. Hi, I'm the guy who made the MIDI DAW controller. Finally caught your stream today. Oh, from Facebook. Yeah. I'm going to post you up there because that's it's really cool what you did. So, welcome. All right. So, this is our normal MIDI circuit. And normally we would put a 220 ohm resistor here, a 220 ohm resistor here, and a 220 ohm resistor here. Okay, and that's our circuit. Now, how do we figure out what's going on here? That's a good question. So, what we need to know, first of all, is what we call the forward voltage, or the VF of this diode. Okay, and that's going to play a very important role in what we're doing. So let's pull up a data sheet, because data sheets are fun, aren't they? And let's scroll down to, there we go, electrical characteristics. So VF, it's saying typically it's 1.4 volts and maximum will be 1.7 volts. And that's going to be important in a sec. So let's start, we'll use the typical version. So what that means is, you know, if you buy a whole handful of these, a lot of these will be 1.4 and a couple maybe 1.7. All right, so we'll use the 1.4 value there. Okay, so now we can actually figure out what's going on in the circuit. So to calculate, before I do that, here's one little thing you should be aware of. So this line here with the 0 volts is actually the TX line of your microcontroller. So this is what's outputting the data. Now, as you may know in MIDI, usually it hangs out at 5 volts, and then when it starts sending data, it drops down to 0 and it kind of sends a waveform like this. And then when it's done, it goes back to 5 volts. So 5 volts is its normal state, 0 volts is its low state. So what happens when this is at 5 volts, when there's no data being sent? Well, if you look, we basically got 5 volts here, we've got 5 volts here. So there's no voltage different in this circuit. So no current's going to flow. So the circuit's basically off, right? So it's not doing anything. So all we have to do is calculate this for our 0 volt state. All right, so when it goes low, when there's data coming through, the voltage, here's a ground, here's 5 volts, so there's going to be a current flowing through the circuit in this direction, and it will come out here, so all the way around. Okay, so that's kind of what's going on. So now we can actually calculate what the current is in this circuit. So what we have to do, if you remember, Ohm's law states that current, we'll indicate that with I, equals voltage divided by resistance, right? So first of all, we have to figure out what our voltage is. So you may say 5 volts, but that's not entirely true, because remember, we have a diode drop. So our LED is actually dropping 1.4 volts. So our actual voltage running through the circuit is 5 volts minus 1.4 volts. All right, that's our total voltage. then we divide that by our total resistance, which is 220 plus 220 plus 220 equals 660. And that's ohms. Okay? So what does that equal? So all we have to do is get our handy calculator and type all this in. So we got, turn it on first, that helps. We got 5 volts minus 1.4 volts equals 3.6 volts divided by 660 ohms gives me 0.0, there's a glare, 0.005454. So why don't we round that up to 0.0055. Now, in electronics, we wouldn't generally, and that's, sorry, amps. In electronics, we generally don't write things like that. So what we do is we move the decimal place 3 places to the right, and this becomes 5.5 milliamps. Okay, so there's our current going through the circuit if all the values are like this. Now, you may know that the MIDI specification basically states that the current should nominally be 5 milliamps. Let's see, if I remember correctly, my MIDI in on the RX1 spat out the data to TX like a MIDI through, not what I wanted. So let me get your name, Sir Christopher. Sir Christopher is saying that MIDI, you're probably using the MIDI library, right? And that's kind of a feature of it. So the MIDI, let's see, the MIDI on the RX spat out the data to the TX. Okay, yeah, so that it's acting like a MIDI through. Okay, so it's basically, it's acting like it's what we call a soft MIDI through. So it's basically mirroring the commands on that it receives to the output. So it's actually passing things through. You can actually, there's a setting in the MIDI library that you can set to disable that, so it won't do that. So just Google Arduino MIDI library MIDI through, and you should figure out how to do that. All right, where was I? What was I doing? Oh yeah, so the MIDI standard says it nominally puts out, I can't say that word, puts out 5 milliamps. That's the spec, right? Now, you got to think of the word nominally. I can't say it. Oh my God. That doesn't mean normally. It means in name only, but not maybe how it actually is. All right, so there's something to think about, and we're going to look into that because people get really uptight about this figure, and there's probably a good reason, because they're thinking, oh my God, if my circuit puts out more than 5 milliamps and I plug it into my, Dave Smith Prophet 8 and I blow it up, I'm going to be sad, right? And no doubt you would be, right? But we're going to look at why this 5 milliamps isn't always the case, all right? So as you can see in our first example here, we got 5.5 milliamps, right? So we're already a little over, but still close enough, right? Okay, now here's one more little thing. Let's go back to our data sheet. So as it says, our forward voltage VF is typically 1.4, maximum 1.7. So that means there's a range, and it could change. So what happens in that case? So in that case, let's get rid of this, and we're going to change that to 1.7 volts. So let's say, I pick a, kind of an odd chip out of the bin, and I get 1.7 volts. Then my calculation is going to change a little bit. So 5 volts minus 1.7 divided by 660, and that gives me exactly 5 milliamps. All right, so in that case, I'm right at spec. Okay, hopefully that kind of makes sense what we're doing. But now we've got to change things because we're no longer in the 5 volt world, we're in the 3.3 volt world. All right, so let me get rid of some of this stuff here. Okay, so like I said, we're no longer in the 5 volt world, we're in 3.3 volt world. Okay, now the only thing we can really change is these two components here, right? We can't touch anything over here because that is in your device, that's in your synth, and we can't touch it. The only thing we can touch is our out, which is all right because the out kind of drives the whole circuit. So as you can see, the voltage from the output goes through both devices, and at no point is this guy providing any voltage to this circuit, right? All the voltage from the MIDI input is actually past the optocoupler in the main circuit. So the MIDI output is driving this whole deal. Okay, so let's do a little test here. So what if we calculate this? So if we find our current, 3.3 volts, minus our diode drop, 1.7 volts, divided by 660 ohms. So let's calculate that, and I think we're going to be disappointed. So that gives me a total of 2.4 milliamps, which is way below our spec. That's not acceptable. All right, so we already know we got to make some changes. And let's put our thing back to our nominal level, or our normal level, 1.4, the typical value of this. Okay, so what we have to do is change the values of these, but to what? That's the whole question, right? Okay, so there's a couple of schools of thought here, and this is where I'm kind of having to do some research. First of all, if we go to the Teensy actual site, right, so this is the guy, I think his name is Paul, who designs this, and he's way smarter at this than I will ever be. But he's saying for Teensy 3.0, which is all the 3.3 volt device, use two 47 ohm resistors on MIDI out. Okay, simple enough. So let's see what that does. So he's saying use two 47 ohm resistors on the out. Okay, so our total, we have to recalculate our total resistance. So it's 47 plus 47 plus 220 equals 314. Okay, so let's calculate our our current now. So minus 1.4 divided by 314 So that would give me approximately 6 milliamps. All right, so higher than spec, but as you can see, the spec really is variable because we don't really know what device we're plugging into, right? This one has a forward voltage of 1.4. It could have a voltage up to 1.7. It could be a totally different device that has a different forward voltage. So we don't really know, right? So we're designing for kind of best and worst case scenario. So I would say that's kind of cool, and that's pretty good. But, there's always a but. Let's check out this. Where is it? The official document produced by the MIDI Manufacturers Association. An update. So they're aware of all this 3.3 volt stuff. So they put out an official document. So let's go down. Details. So all this stuff is kind of MIDI is a circuit with a 5 milliamp current loop logic. Oh yeah, that's kind of what we thought. So it's saying Sharp PC900V op amps, or sorry, opto couplers and 6N138 opto couplers have been found acceptable. The receiver must require less than 5 milliamps to turn on. That's important, and the rise time should be less than 2 microseconds. All right, so these two op couplers and some others satisfy that. All right, so it gives you a new circuit, right? And it adds some ferrite beads and stuff, but we're going to disregard those for now. But there's our two resistors. There's our voltage in. There's our TX pin driving this resistor. Look what they're saying. For 5 volt, use 220 ohm on both resistors. For 3.3 volts, use 33 ohms and 10 ohms. All right, so that's different than what Paul from the Teensy site says. So let's try that. So we're going to say, the Teensy site suggests a total resistance in the circuit of 314 ohms, whereas the MIDI site, we'll say MD, and we'll calculate that. So okay, so that's saying use a 33 ohm resistor here and a 10 ohm resistor here. Now what's that going to do to our lives, you might ask? So 33 plus 10 plus 220 equals 263. So they're suggesting, what am I doing? 263 ohm circuit. Okay, so let's see how that changes our thing here. So we got 3.3 volts minus 1.4 volts gives us 1.9 divided by 263 gives us a total of 7. Yeah, I'll do 7.2 milliamps, right? Which is a bit higher than the 6 milliamps we got with the Teensy suggested values. Okay, so that leads us to a little interesting issue that we have to figure out. What's the better version? So let's dive back into this a little bit. Okay, so let's look here. Low voltage signaling details. The MIDI current loop can run at a low voltage, 3.3 signal levels. The MIDI out circuit is the only affected component for low voltage signaling. It requires changing the output resistors from 220 to 33 and 10, and it's saying use plus minus 5% resistors, and changing the voltage to 3.3. Okay, so let's see their reasoning behind that. So technical notes. So from the viewpoint of the transmitter, the opto isolator is electrically identical to an LED in series with a 220 ohm resistor. And that's exactly what we were showed, right? There's our 220 ohm resistor in series with one LED. Opto isolators found in some MIDI devices. Now this is the important part, okay? So opto isolators found in some MIDI devices have an LED maximum forward voltage drop of 1.9 volts, right? And can require up to 5 milliamps typical current drive for normal operation. The actual required current is opto isolator dependent. So it's saying, for example, the PC900V, which is another opto isolator, has worst case forward voltage current requirement of 4 milliamps. Okay, so that's kind of their thinking. So let's go back to the board and kind of plug those numbers in and see what happens. So they just said that a worst case scenario, you can get a VF of 1.9 volts in certain opto isolators. Okay, so let's see what happens there. So we'll change this to 1.9. Now, first of all, let's use the Teensy value of the 47 ohm resistors. So we get a total of 314. And let's see what happens there. So 3.3 minus 1.9 divided by 314. Okay, look at what we got. We got 4.4, so let's call that 4.4 milliamps. All right, that's kind of low. We're actually dipping down below the MIDI standard now. And if you remember this, it's saying some devices can require up to 5 milliamps typical for normal operation. So what that is saying is that our 4.4 milliamps may cause some weird errors in certain devices, which would be bad to say the least, right? Because it may kind of work, but it may kind of, cut out intermittently, and you're kind of scratching your head going, why, what's going on? Also remember too that we could have up to a 50-foot MIDI cable in here that's going to add a few ohms of resistance, maybe 2 to 4 or 5 ohms resistance. So we're actually going to drop this down a little more. Now let's do the same calculation with the MIDI document suggested value. All right, and we'll see what happens. So that's 263 ohms, and we'll see what we get. 3.3 volts minus 1.9 volts divided by 263 gives us a total of, let's call that 5.3 milliamps. So we're above kind of our MIDI spec enough that if a device was really really sensitive to anything below 5 milliamps, this would probably still drive it. Okay, so that's kind of a check mark in the favor of this guy, right, of the MIDI values. Now this is kind of a really bad case scenario, like 1.9 volt forward voltage is rare, and I've kind of done a little there's so much glare there. A little list of the common opto isolators you may use for a MIDI circuit. And the VFs, like say a 4N28, which is a really old school one and probably not used as often anymore, has a typical VF of 1.3, a maximum of 1.5. The PC900, which we talked about, has a typical of 1.1 and a maximum of 1.4. The 6N138 that I've been using in my projects has a typical of 1.4, a max of 1.7. And the 6N137, which is you may have used if you're a fan of mutable instrument stuff, has a minimum of 1.1, which is low, and a typical of 1.7 and a max of, a max 1.7, typical 1.4. Okay, so that 1.9 is kind of not showing up in any of these guys, but there are other devices you can use, right? And that's where I think they're taking it from. Also, temperature can have an effect as well, right? So they're kind of going for the nightmare scenario, and seeing if this will cover it, right? And I think that's their thinking behind that. Another thing they're also thinking is, not every power supply is going to give you a perfect 3.3 volts, right? Maybe plus or minus a few percents there. Like we said, also they're using 5% resistors in all these guys. So this value could be a little higher or a little lower, right? So let's kind of think, if we take our total here and we say we're really unlucky and we pick some real bum resistors that are as far out of spec as 5% will allow us. That would bump my resistance up to 276. And if I say my power supply was sagging a little bit by 5%, minus 5%, so that would bring me down to 3.1 volts. All right, so if we calculate that, that's like, worst case, everything is against you, like you've got a voodoo curse acting on you, and you're the unluckiest person on the planet. But you never know, you got to calculate these things. So 3.1 minus 1.9 divided by 276 would knock my current down to 4.3 milliamps, right? So even with these lower values, if everything's against me, I can get way below MIDI spec. So that's kind of the way that I believe they're thinking. They're thinking of nightmare scenarios. And I was on the wrong thing for that whole explanation. I'm sorry, guys. But yeah, so basically, my power supply sagged down 5% to 3.1. My resistors were over spec by 5%, which they technically could be. You'd have to be real unlucky, but they could be. I would get a total current in this circuit of 4.3, which, if, like they're saying, my device needs 5 milliamps to behave, could cause real problems. But if I had the 47, it would be even worse. I'd probably be into the 3 milliamp range, right? Which would be totally out of the question. So what the MIDI guys are doing with these values is they're designing for nightmare scenarios, just the worst possible scenario. Grab a drink of water for a sec, guys. So yeah, that's kind of what they're thinking, which is a good way to think. But there's one more thing we have to think about. What about the other nightmare scenario, which is if we go too high and we fry something, right? That's a nightmare scenario of a whole different kind. So let's play with some values, okay? So let's say my MIDI input was all good at 3.3 volts. Now, my lowest VF I found was around 1.1. All right, and that's kind of like, you know, a minimum on a few devices. And let's get rid of this. So we got 1.1 volt VF. And we'll check it with the normal. We'll pretend all our resistors are exactly what they say they are. What current will I get? 3.3 minus 1.1 divided by 263. We get a whopping 8.4 milliamps. All right, so that's you know, that's high. Like our spec is 5 milliamps. We're getting 8.4. But remember, you know, the 5 milliamps isn't something that's gonna occur very often. You're often gonna be above, as we kind of discovered. And this is, you know, kind of the lowest we can expect. Now, would we fry something with this? That's the question. Let's go back to some data sheets and see if we can get an answer. So let's look at the 6N138, which is real common. We'll go to the absolute maximum ratings. Okay, so for forward current absolute maximum rating is 25 milliamps. Right? We're nowhere close to that. We're like 8.4. Even in our worst case scenario, we're not really close to the maximum of that component. And in a MIDI circuit, really that's the only thing you're going to fry is this diode here, right? If we're going to fry anything, the resistor should be fine with, you know, with whatever within reason we put into it. So that's okay. And if we look at my list here, the maximum current of a 4N28 is 60 milliamps, right? PC900 is 50 milliamps. 6N138 is 25 milliamps. And 6N137 is 20 milliamps. So the worst case is 20 milliamps here. And not that you should ever get anywhere close to that, right? If you're designing a device. Like that's like worst case, you know, if you go above that, things are gonna die on you. So you wanna keep it below that to a good margin, right? So maybe even half that. So in this worst case scenario, say I take half, that's still 10 milliamps, and you know, my nightmare scenario was 8.4. So we're still pretty safe, right? So once again, the Midi 5 milliamp nominal rating is truly a nominal rating, which means it's in name only, right? Not really how things work in the real world. So our question that we have to answer is which side are we better to make a mistake on? Do we want to be too high or do we want to be too low? Now, as we've seen, we're kind of skirting around the low end. You know, if like our VF gets a little too high, we're getting dangerously low, right? On the high end, we have quite a bit of room. Like even our worst case scenario we could come up with, you know, let's even bump it up to 9 milliamps. We're still pretty safe, right? We're still under 10 milliamps. So it seems to make more sense to me to err on the high side rather than the low side, because if we err on the low side, we could get a really flaky instrument that's not functioning well. Whereas if we err on the high side, we're pretty safe, okay? And we're not really taking into account like capacitance or extra resistance by a really long MIDI cable run. We're not even taking that into account. So for me, my vote right now is going with the Midi spec instead of the Teensy site spec. You know, that's kind of what I'm thinking. And I'm kind of looking for something to change my mind on that. Some reason to say, oh, this is why they went with this, right? Now, the only thing I can think of is the Teensy, like if you're familiar with Arduinos, like I think the output current on a single pin is about, I believe, 25 milliamps, right? So on a single pin on an Arduino can comfortably source 25 milliamps. Now I know on the Teensy board, it's not using a Atmega AVR chip. It's using a Freescale, what do you call them? ARM chip, a Freescale ARM chip. And so what I believe is the maximum, and I'd have to double check this, but I think it's 20 milliamps maximum current on a single pin, but the suggested operating maximum is 9 milliamps, right? And we're close, but we're still under with our nightmare high-end scenario. So maybe that was his thinking, like he wants to bump everything down a little bit to get it away from that 9 milliamp ceiling. And you got to think, like, you know, this is the 20 milliamps is maximum. This is the recommended maximum. So what does that mean? So let's say you design a bridge that can take technically 20 tons, and you drive a tank across it that weighs 19 tons. That's a little scary, right? That's a little scary. So instead, if it can rated for 20 tons and you drive a truck across it weighing 9 tons, you know, you're pretty safe. You've got a quite a good margin of safety there, and that's kind of what this recommended maximum is. It's saying, hey, you know, keep it under 9 milliamps and you should be safe. Everything will be good. And I think, you know, we're under 9 milliamps, right? With a really terrible situation we came up with. So that's my thought. So I'm thinking of going with these values in my design. And what I'm going to do is maybe I'll reach out to Paul at the Teensy site and kind of get his thoughts on this. Like, you know, why did he choose the 47 milliamps, or sorry, ohms for these two resistors, whereas the Midi official document for 3.3 volts is calling for these values, right? So what's his thought behind these guys? Why did he choose that? And if he's got like, oh, it's an obvious reason, then yeah, that makes sense. If not, I'm thinking this makes more sense. So there you go. That's kind of a glimpse into the complications of my life. But you know, you got to think of this stuff. It's like eating your vegetables, right? It's not always pleasant, but it's good for you, and it's going to make your design work well, and hopefully lead off any weird problems that would happen if people in the wild start plugging it into stuff. So there you go. Hopefully that kind of makes sense. I just want to kind of show you guys this in this stream because you know, I think it's important to kind of see the process a little bit, and hopefully, you know, by putting this out there, you know, people will comment back and say, oh, this is why you're wrong, this is why this sucks, this is the, you know, like, there's always good reasons, there's always people who know more, and it's good to hear from them. So guys in the chat, anyone any questions? Who's that? William. Oh my God, with a donation. What a guy. Good Lord, man. Thank you so much. That's awesome. Thank you. You just bought my optocoupler here. Awesome, man. Thank you. So any questions from you guys? Any thoughts? Any or have I numbed you all into a stupor with this all this calculating? So like I said, I'm building a and you may have seen it in the last video. It's this cool whammy pedal, Digitech whammy pedal mod that's going to control the whammy pedal, and it's I've got it on another live stream. You can watch the VOD. I think it's gonna be really cool. I've been doing some more work on it. Really happy with the results. You know, but I gotta figure this MIDI stuff out because I gotta write the schematic and I gotta figure out what exactly to tell you guys to use for these resistors. All right, so what's that, Sir Christopher? This is the sort of granularity I love so much. Well, thank you. I'm glad you do, because yeah, this is the kind of stuff, you know, I tell most people and they kind of glaze over and they look at me and it's like, yeah, okay, whatever. So what's that, Joseph? Why should the resistance 3310 be higher on the 3.3 volt side? That's a great question, Joseph. Daryl, really appreciate the insights and process for analysis. Thanks. So Joseph asked a really good question, and that is, why is this the high one and this the low one? And does it matter? Could I switch these around? Because if you kind of look at the circuit, it doesn't really matter, right? Or you would think. But there is a reason behind that. And the reason is they are kind of planning for another disaster scenario. And I'm very glad you brought that up, Joseph. So what they are planning for, hey William, you're up on the board. Congrats, man. So what they're planning for is one of the contingencies of MIDI is some sort of short circuit protection. So you picture like this right here between these two pins is your MIDI cable, right? With these exposed pins. What if I'm like goofing around with this and I accidentally stick it on a coin or something falls in it and shorts it out, right? Shorts it right to ground. So that is kind of the nightmare scenario. So we got 3.3 volts through our 33 ohm resistor and then right to ground. That's kind of a dumb way to do ground, but okay. So that's what would happen technically on an electrical whatever situation. Good word. So what would happen? So 3.3 volts. Turn it on first. 3.3 volts divided by 33 ohms gives me 0.1 amps, or let's see, 1, 2, 3, 100 milliamps, right? So that's bad, right? So that's why they want, okay, so that's what would happen. But why, what about here? Couldn't the same thing happen here? Right? Sure it could. I could short this one out just as easily. So why are they more concerned with this one? Well, they're more concerned with this is because this is being fed directly from a power supply, right? This one is being fed by the output of something, a microcontroller or a buffer or something, like a buffer IC or something. So this one's being buffered, this one isn't. It's coming straight from the power supply rail. So this one has a little protection built in. This one doesn't. So that's why they put the bigger one here. And I think they may say something about that in the thing. So yeah, they got something about it in here. I have to read through it. But yeah, that's kind of the reason. And there's another suggestion that they made now that we're on this topic. So to figure out the wattage of what we're doing here, remember that's voltage times current. So 3.3 volt times 0.1 amps would give me 0.33 watts, right? Now, we've kind of assumed that we're going to use quarter watt resistors, right? Which, if you remember, a quarter watt resistor is a maximum of 0.25, wow, that's really messy, equals 0.25 of a watt, a quarter of a watt, right? So technically, when I short this guy out, I'm in danger of blowing up that resistor. And that is why in the MIDI document, they actually suggest you use a 1/2 watt resistor for that 33 ohm resistor, which would give me a maximum range of 0.5 of a watt. So that this guy would survive. This guy probably wouldn't survive. So that's for Joseph, that is why we're using the bigger value on the supply rail. Excellent question. Thank you. So any other question, guys? That's a lot of to digest, man. That's a lot of me talking. So thanks for hanging out once again. I'm really enjoying these live streams, especially on YouTube. Have I dropped any frames? No, I don't think so. I don't think I've been stuttering, and everything's been good. So once again, remember to subscribe on YouTube. I got a great YouTube community going. Visit Notes and Volts, Twitter. Subscribe on Facebook if you haven't already. Like, you'll be able to watch this geeky stuff and, you know, all day. What's that? Some more questions coming in. William asks, would level shifting up to 5 volts and using the recommended resistance for 5 volts make a difference? It would allow you to use the regular values, the 220 ohms values. Technically, it's going to add more stuff to your circuit. Like, you're going to have to do level shifting, which is you know, going to add more cost, more parts, more hassle. There could be a problem with current, right? Your level shifter, if it provided its own current, it should be okay. But, you know, it's not, as we've seen, we can change 2 resistor values and make our circuit work, or we can get into level shifting and all that hassle. So for me, like, the resistors make way more sense, and level shifting would just be kind of a pain. And especially if you're powering your circuit like through a regulator that's giving it 3.3 volts, and everything's 3.3 volts, and all of a sudden you gotta bring in something to drive up to 5 volts, you may have to redesign your whole power supply. So that's, you know, we're taking the simple solution over the more costly, complicated one. Joseph, good answer, thanks. So this helps protect the power supply. Okay, have a great week. Have a great week, Joseph. Great questions, guys. Really great. Had a lot of fun. Remember, Patreon, let's see, yeah, I guess it does make more sense. I'm kind of a newbie to all this. Thanks for answering my question. No problem, William. Thanks for asking it. Remember, Patreon, if you guys like what I do and you want to support, that's a great way. So take a look. I've got my top patrons. I'm going to put them on this board. Let's just wait for them to come up. And you get your shot at fame. So thanks to these guys. They are awesome. They're really helping me continue to do what I do. So anyways, enough of my shilling and nonsense. Oh, and if you like the music at the start of the stream, go to TechBrain, www.techbrain.com, and you can listen to it, buy it, or take it for free. It's all there for you. Okay, guys, so if no more questions, I guess I will see you next time. Have a good night, enjoy your week, and I'll see you then.